All right. Thanks everyone for coming to this session of the Bajeo, and it's a very big pleasure to have Terry Sultanis here from Juvascular, who's an old friend and colleague, and it's who kindly accepted the invitation, even though it's very late in Finland. So thanks, Terry, and go ahead, please.
All right, thank you, Chucho, for the introduction. It's a great pleasure to accept an invitation from you. And it's not that late here in Finland. It's 8 o'clock in the evening, so like it could be worse, right? Uh, and yeah, I'm happy to speak here. Uh, what I will speak about today, well, the title you see it there. It's Lipschitz-volume rigidity. And it's a topic that I find nice because it's sort of elementary to state somehow. So it's a problem in somehow geometry, Riemannian geometry or metric geometry, if you want, that is kind of easy to state. But then somehow also has surprising aspects or is surprisingly difficult uh, in some ways. And so what I will do in this talk, so first of all, I will keep it non-technical, more or less. I'll try. And that means that I'll try to maybe draw a few pictures and examples. And even though towards the end there will be some kind of statements or theorems results that are kind of technical in nature, I will brush that under the carpet and try to give you guys an intuitive idea of what um, what is going on there. Um, okay, so we start with a classical or folklore theorem, which is just a theorem in Riemannian geometry. So, and the theorem states that if you have a one Lipschitz map, surjective map between two manifolds, closed oriented manifolds equipped with a Riemannian metric, so that the volumes agree. So you have a one Lipschitz map between closed manifolds with the same volume, then this map actually is an isometry. It's an isometric homeomorphism. Okay, and here isometric, by the way, means I think in yeah. So in this case, isometric means like that it is distance preserving. If f if we required f to be smooth, we would get a Riemannian. We could get a Riemannian isometry in addition. So a smooth Riemannian is isometry. And just as a reminder, I'm sure everyone knows this, but what Lipschitz maps are. So Lipschitz map between x and y is a map that distorts the distances by at most a factor of L. And then you call it L Lipschitz. And here in the theorem, it's one Lipschitz. Okay, so this kind of theorem or result is an example of a rigidity statement, in this case in Riemannian geometry. And this one is called Lipschitz-volume rigidity because it involves Lipschitz maps and the volume. Fair enough. And I mean, it's one in a long line of examples of rigidity statements. So there, like typically when you have some kind of geometric inequality, then the extremal cases come oftentimes with a rigidity statement. So you have some, for example, the isoperimetric inequality, just in Rn, for example, in case of equality, then the set has to be a certain kind of thing. Is there a question? If so,
Yeah.
then
Well, hi.
yeah.
Hi. Nice to
Hi.
meet you. What is the usual interpretation of the Lipschitz LDX? What's the usual interpretation that takes for a classic example
Sorry, what is the usual interpretation of the Lipschitz condition?
of the Lipschitz function
I
in,
mean, yeah, I
in
think,
some example?
well, so for example, linear maps between Euclidean spaces are Lipschitz functions. They are perhaps some of the most kind of easy examples or best behaved examples. But in general, Lipschitz map it just distorts the distances. So the image points do not go farther away than the original points, or at most L times more far away. So for example, a rescaling by a constant factor is an example of a Lipschitz map, or a translation, or well, an isometry, obviously, it's a Lipschitz map, and so on. So there are many examples. Yeah. And
Thanks.
in fact, like a C1 map, if you have a C infinity map, say, between compact manifolds, then this will in particular be a Lipschitz map.
Okay.
Yeah. All right. So the basic gist of it is that these Lipschitz maps tell you something, or they carry some information about the metric geometry because they respect the distances somehow, more or less. But in fact, because you don't have the other inequality here in this condition, they can collapse things. So, and this is somehow the why this folklore theorem is not just some obvious statement. Yeah. But okay, so this Lipschitz volume rigidity is an example, is one example of these rigidity statements. You have a Gromov-Bishop inequalities there. Also, you have a rigidity statement that in case of equality, something specific happens, and so on. And these are very they pop up in Riemannian geometry a lot, and are therefore somehow important. And as a last hand wavy point here, this particular rigidity statement and also the some other ones are important. So it's oftentimes important to know that they pass to some limit. So when you take a sequence of spaces that converges to some limiting space, then these inequalities remain true under appropriate conditions. And what this does is take us this stability considerations, taking limits of manifolds, for example, it takes us out of the realm of manifolds. So a limit of manifolds is not a manifold anymore, generally speaking. And so it brings us to metric spaces. And no, so in metric spaces, you can ask the same question, but of course, a slight difference is that with Riemannian manifold, you have a natural notion of volume. Now, in a metric space, it's not that there's some canonical volume. You need to decide what you mean by volume. And here, for this question, I decide, or people have decided to use something called the Hausdorff measure. And let me just state the question again here. So you have two metric spaces that have the same Hausdorff measure, Hausdorff n measure for some integer n. And we also assume that this is not zero and not infinity, because otherwise this doesn't really carry any information, this equality here. And you have, again, a one Lipschitz surjective map. Another question is similarly to the manifold case, is this F also an isometry? And notice that in this case, when you're talking about metric spaces, I mean, an isometry is the best you can possibly hope for, because there is no smooth structure or anything like that. So it doesn't mean anything to say, like there is no notion of Riemannian geometry or things like that. So somehow an isometry is the best you can do. And for those who aren't that familiar with Hausdorff measures, here's a quick definition. So it's just what you get when you cover your given set by sets with smaller and smaller diameter, and then you take the sum of the diameters of the set to some power s, which in this rigidity question people usually take to be some integer. And the upshot here is that if X is a manifold, a Riemannian manifold, then this Hausdorff measure, n measure, is the n-dimensional volume of the manifold. Okay, so that's the question. The folklore theorem says that the answer is yes in case X and Y are closed Riemannian manifolds. But as you might imagine, in general, the answer is no. And so here are some counterexamples that I will try to convince you with that the answer is indeed no. So the first is somehow very easy, and it's still kind of stays in the realm of manifolds, more or less. So if you look at the identity map between Sn as a manifold, so equipped with an intrinsic metric, and you take the identity map to the same set, so the map doesn't do anything, but you change the metric. So now instead of looking at the intrinsic metric, you look at the induced metric, so the metric inherited from the Rn plus 1, so the space inside which Sn lives. Now this is a one Lipschitz map because the intrinsic distance is always larger than the Euclidean distance. And it's also volume preserving. This is kind of a nice exercise to do in case you feel like doing it sometime. But the basic reason is that when you fix a point on the sphere and you look at smaller and smaller radii, either with respect to the Euclidean or intrinsic distance, they start to look more and more flat, and therefore the metrics look closer and closer, like they become closer and closer. And because the volume somehow measures like infinitesimal behavior, the volume is actually preserved. So the volumes of these two things with respect to the so let's say the Hausdorff n measures of both spaces with their respective metrics are the same. But clearly this is not an isometry, right? It is a bi-Lipschitz map, but it's not an isometry. And the second example is something I call the discounted line. So here's an explanation, but perhaps it's better if I try to draw a picture. And the picture is like this. So you have a sphere, and then you have another sphere. They're supposed to be the same size. They're not here, but that's an accident of me not knowing how to draw. And the map goes from the sphere again to the sphere, and it's the identity map, I guess, again. But now I take some line segment here inside in the target space. Let's say I take this line segment, and on this line segment, I declare the metric. I do a kind of conformal change of metrics, but not a smooth conformal change of metrics. I say that in here, the way like to travel along this line segment, you only pay an epsilon amount, or let's say 1/2. So the distance between these endpoints with respect to this new metric is not whatever the length of this guy originally was, but half of it. And then everywhere else, the conformal factor is 1. And now then you again look at the identity map, and you see that because you made it cheaper to travel along this line, the map you get is again 1 Lipschitz, so it does not increase distances. And moreover, the conformal factor everywhere else is 1, and so this is away from this set. This is a local isometry, and this set has 0 measure. So this again, it preserves volume. And I mean, here is the same thing in a bit more mathematical terms. And so you can define the metric by looking at lengths and then infimizing over the lengths of curves joining two given points, and that's how you define this metric D. So this is not an isometry. And then lastly, there's this Pacman example. There is perhaps Pacman example, and let me try to draw something about that one as well. So you now take the closed disk and you remove a slit. So this slit that I drew here, you remove it. And the space is everything out except the slit, and you equip it with a length metric. So to go from here to here, you have to pass through here. And so the distance between these 2 points is not whatever this is, but it's whatever this is, right? And then, because now you have an open set, you take the completion, and then you get a compact set, a space. And then what you do, again, these are supposed to be the same size, the circles. Then you have a map which just takes a point and sends it to the corresponding point on the unit disk. Oh, this does not work. Like this. And everywhere else, the map sort of isn't doing anything special. It just identifies the point here with the corresponding point. And only along this line, what it does, you have two copies of each point on this line. One copy if you approach from this side, and another copy if you approach on this side. And both those points it sends to the corresponding point on the line. And this is again a one Lipschitz map. And again, because this is locally an isometry and this bad behavior sort of happens in a zero measure set, again, this preserves volumes. All right, and the reason I call this Pacman is because somehow one way to visualize this is that if you can sort of think that you take the disk and you take the slit and you push the different sides in different directions, and then look at the length metric on that surface. So it kind of becomes like an opening mouth. But yeah. Okay, so let me go back to here. And do we have a question?
No, I just
No question.
I wanted
Okay.
to say they're very nice examples to keep in.
Yes. Okay. Thanks. Yeah. These are kind of like the prototypical examples what can happen. And then perhaps my personal favorite example is a torn football. So what is happening here? You take again the sphere, but now you know tear a hole as in the picture, and let's say we equip this with the length metric again. So now this is a sort of surface that is again locally isometric outside this where this bad the tearing happens. And then you define a map from this space with a length metric to the standard sphere by just gluing this back. So you fix this tear. And so this point, I don't know, can you see the mouse or the hand? I guess.
Yeah.
So.
Yeah.
Yeah. So this point and this point are the corresponding points here. They get mapped to the same point, and everywhere else, the map just is one-to-one, a local isometry. So, I mean, the principle is actually kind of similar to the Pacman example. So that way you get, again, a Lipschitz map, and again, it preserves volumes, but this one is same as this, the Pacman example. This one is not very far from being an isometry. It's not even bijective. Okay, so let me recap what kind of went on in these examples. So okay, the first example with the non-intrinsic metric, what went wrong is that the metric in the target is not intrinsic, and that's a first obstruction. This is a kind of an easy obstruction to realize once you think about it a little bit. But then in the second example, or sorry, I go from last to first. In the last example, actually the last two examples, so the torn football and the Pac-Man example, what kind of happens is that the domain space that you start from, it sort of has some extra boundary. So in this picture, you can kind of clearly see this thing is a kind of a boundary on the space, but when you map it, it disappears because you glue the things together, so they cancel the boundary sort of can or the boundary cancels itself out, and and this creates the problem. And so actually, something similar happens in this Pac-Man example because the slit that you cut along, this becomes a boundary. You count it twice, but then when you map the thing to the standard closed disk, the boundary cancels out. So that's one thing that can go wrong. And another thing is this possibility of having like some exceptional sets, some sets of very small sets, like sets of measure zero. In the examples, they were even like lower dimensional, but in general, you might they might be bigger than that, but still like zero dimensional, zero measure. So that you have these exceptional sets where it is very cheap to travel. And that's, well, I wrote the first example, but it's the second example. So there you have this null set, this line segment, and you made the line segment, you gave a discount for curves traveling on it. You said that instead of having length or conformal factor 1 there, the conformal factor is something strictly less than 1. And so there what happens is that when you take 2 points, not necessarily just on the set, on this line segment, but somewhere close by, then but still, so 2 points that are close to the line segment, closer to the line segment than they are relative to each other. So then what happens is that the geodesics joining those 2 points will always travel along this line segment. And so what you've created is you've created this exceptional set that geodesics between nearby points always travel in that null set. And this then breaks the volume rigidity, Lipschitz volume rigidity. And this phenomenon is not present in the smooth case, but it is very present in the non-smooth, like in the metric case. All right. So let me say just a few words about the proof of the folklore theorem, right? So the statement is that you have this surjective one Lipschitz map F, and between two closed Riemannian manifolds, M and N, and the volumes are the same. So first of all, from the one Lipschitz condition, you in particular get that the length of the image curve of the image curve of gamma the lengths do not increase. And this somehow translates to saying that the Jacobian of the map, so the determinant of the differential, but the absolute value of it is at most 1. Okay? And then from the area formula, so the area formula is this thing in the middle, right? So that when you integrate the absolute value of the Jacobian, it is the same thing as so you integrate that over the domain side. It is the same thing as integrating over the target side, the number of pre-images of the map. Okay, but now because this determinant is at most 1, then the volume of M is not going to be smaller than this guy. And then here the area formula gives the equality. And because you assume that F is a surjective map, then every point has at least one preimage. So this is at least the volume of M. But now the assumption was that the volume of M and the volume of N are equal. So both of these inequalities are equalities, actually. And then what that tells you is that the number of preimages of almost every point is 1. And this the absolute value of the Jacobian is also almost everywhere 1. And this is somehow, when you have a Lipschitz map, that's what you can say. You cannot say anything more about this because it might not be differentiable everywhere a priori. Oops. Okay. I don't know what I'm doing.
Sorry, I have another question.
Yes.
In the volume, is the usual volume as a manifold or has another interpretation?
So this here is just the usual volume as a Riemannian manifold.
Okay.
But it happens to coincide with the Hausdorff n measure over the manifold viewed as a metric space. But yes, it's the standard volume. And now if
Como que it reduces the space, something like that, the F map, no?
Sorry, can you say again?
Yeah, in some sense, the function reduce the manifold when it's Lx function. In some sense, the function reduce the manifold, the image. But in some examples, for example, like sense of value, absolute value of x, this is why you meant. This is what you mean that we have some singularities.
Yeah, so the map itself is continuous, but because it's only Lipschitz, it might not be differentiable everywhere. But there's this theorem that's called the Rademacher's theorem that tells you that it is differentiable almost everywhere. So basically what I'm saying is that under this assumption of one Lipschitz, this df, it doesn't exist everywhere, but it exists almost everywhere.
Okay.
And somehow it's not, I don't know if I'd call it singularity, but it's like a non-differentiability phenomenon. But anyway, this area formula now gave us this thing. And now if it so happened that f was smooth, then actually, so you have that the Jacobian absolute value is 1 almost everywhere. But if f is smooth, then the Jacobian is also smooth, or in particular continuous. And then you have a continuous, the Jacobian is continuous and has absolute value 1 almost everywhere and therefore everywhere. And then because the M is orientable, the Jacobian cannot change sign. So then it's either 1 everywhere or -1 everywhere. And then this would give you that if f was smooth, that would then give you that actually that means that the length of every curve is preserved. Now, because we have this issue that this is not almost everywhere defined and this Jacobian is not a continuous thing, you cannot unfortunately deduce that from this fact that it cannot change sign, for example. You cannot directly deduce it. But you can actually still use this to see that this map F, even if it's Lipschitz or one Lipschitz, under these assumptions, it preserves the length of not necessarily all curves. You don't know that a priori, but you get it for almost all curves. And what does that mean, the almost all curves? In this context, what it means is that so there's some fixed null set, the null set that's coming from the exceptional sets where these two things fail. and you have this equality of the length preservation for all curves that do not spend any positive time in that null set. So here we see this phenomenon that you have a null set, and you look at if you have curves that pass through it, like spend a long time in it or some positive time in it, then those are exceptional curves. For those curves, this equality might fail, but for all other curves, the equality will hold. And the point is that this exceptional family of curves, that is a small family. So all the curves that pass through this line segment, for example, spend a positive time in the line segment, they are a small amount of curves. And in particular, in the classical case, you can also, in a manifold, you can also then perturb the curve a little bit to not spend any positive time in the given set. But so in here, now in the smooth case, the local degree theory now takes us forward. So from this length preservation and these two facts that the preimage of almost every point is 1 and the local index of f is 1 almost everywhere, or has absolute value 1, you can actually deduce that this f is a local homeomorphism. And then from that, you together with this length preservation, you get that it's actually an isometry. So I mean, I'm skipping details there, obviously, but that's the gist of it. And this is nice and dandy in the smooth case, or in the classical folklore setting. So now, if we think about moving to metric spaces, the one immediate thing to notice is that the last step, it cannot, that is not available. So there's no degree theory in general metric spaces. Even pretty nice metric, or somehow pretty nice metric spaces, if they are not manifolds, then there's no degree theory. And as we will see later, even if there is a topological degree theory, it needs to be compatible with the metric somehow. Otherwise, we are still in trouble. But okay. So let me try to go still beyond Riemannian manifolds and enter the realm of, at first, curvature bounds. So you have this setting now, a one Lipschitz surjective map between two spaces x and y with the same n Hausdorff measure. Then the Lipschitz rigidity holds, so that this implies that f must be an isometry in the following cases. So when x and y are closed Alexandrov spaces, so this Alexandrov space means for well, some of you are familiar with it. For those who are not, the Alexandrov spaces are a synthetic notion of sectional curvature bounds. So you should think of them as sectional curvature bounds. And the way they are defined is that you look at triangles in your space. So you pick 3 points and you pick geodesics joining them. And then there's a corresponding triangle in the plane with the same, like a triangle with the same distances. And the Alexandrov condition tells you that the triangle in your metric space is fatter than the triangle in the plane. And that's what it would mean to have Alexandrov curvature greater than 0, greater or equal than 0. And then you compare with different model spaces to define different curvature, like curvature, sectional curvature bigger than kappa. Okay. So it also is valid for metric spaces that are limits, or so-called Ricci limits. So Gromov-Hausdorff limits of Riemannian manifolds with a uniform bound on uniform lower bound on the Ricci curvature and a uniform upper bound on their volume, and also I guess you want a uniform lower bound on the volumes of balls of radius 1, so that balls don't shrink to 0 or don't collapse to like something lower dimensional. And then quite recently, this was also proved, this Lipschitz volume rigidity in the case where these X and Y are so-called non-collapsed RCD spaces. So here the statements are in increasing order of generality. So closed Alexandrov spaces are Ricci limits. Actually, maybe I'm not sure if that's quite true, but at least Ricci limit spaces are RCD, non-collapsed RCD spaces. And here also you have to assume that these are without boundary. So here in the Gromov, in the Ricci limit spaces, they are automatically boundaryless, and here you have to assume it. And then I also want to mention quickly this kind of variant question. So there's a result that relates the scalar curvature and this Lipschitz volume rigidity. Oh, and I see that I have stated the it's not wrong, the statement, but it's too restrictive. So if F is a Lipschitz map or Lipschitz surjection from a manifold to Sn, and the and the scalar curvature is greater than n times n minus 1, then this already implies that F is an isometric, is an isometry. So here what I said, so actually the statement is you don't need to assume that it's one Lipschitz, and that's why this is a variant of the question. In this special situation, if you have any Lipschitz map, so you don't need the one Lipschitz, you just need the scalar curvature bound, and you get that this is an isometry. But that's not really the main focus of the talk now. Okay, so the point of this slide is that there's a way to generalize curvature bounds from Riemannian manifolds to metric spaces, to some metric spaces. And these are called synthetic curvature bounds often times. And in that realm, you still retain some Lipschitz rigidity. And what it basically means is that from the point of view of this question, these spaces with Lipschitz with curvature bounds are well behaved somehow. Okay. Then there are more positive results, and for that, let me just like introduce this terminology. So I call a metric manifold a manifold equipped with a metric, but the metric isn't necessarily Riemannian. It's just some distance. Yeah, and if it's two-dimensional as a manifold, then I call it a metric surface. And the first result for these guys is from Meyer and Dalambekos, also pretty recent, and it says that this Lipschitz volume rigidity holds in this case. So if you have one Lipschitz surjection from a metric surface to a closed smooth surface, so that the Hausdorff 2 measures are the same, then F is an isometry. And you have something similar for metric manifolds also. But so it's the same statement, except you need an additional assumption. You need to assume something technical that's not nice, but you need to assume it, otherwise we don't know how to prove it. And this is due to Denis Martin. So this assumption tells you that, okay, porous sets have Hausdorff measure 0. What is a porous set? A porous set, perhaps I can again draw a picture here. Oops, I guess not. I'll go back. Yeah. Well, a porous set is a set that has holes at every scale, basically. So it means that if you pick a point from the set, there exists a sequence of points converging to that point, and so that the distance of the sequence to the limit point, uh, there is a radius that's comparable to that distance, so that the 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 balls with radius centered at the sequence of points is disjoint from the set. So that means that there are always some holes at any scale you look at. You will see some holes of comparable size to the scale, and it's kind of I mean, it's a reasonable property to have in some way, in like in smooth manifolds in Rn. The Hausdorff measure does have this property, but it's still not what you would like.
I have a question.
Yeah. Yes.
So shouldn't be the case that this set has always have measure zero because of Lebesgue differentiation theorem, or what I'm missing?
So the point is that the Lebesgue differentiation theorem tells you that if you take a set E, then almost every point is a Lebesgue density point, so that the measure of a ball intersected with E divided by the measure of a ball, this ratio goes to zero. And in Rn, this is the same thing as, I mean, this excludes small balls from, like, this forces non-porosity somehow. And so, in other words, if you have a porous set, then each point of that cannot have this ratio, cannot go to 1, and so therefore it must have zero measure. That's true for the Lebesgue measure, for example, and in more generally, it's true if your Hausdorff measure has the property that when you look at Hn of a ball radius r, then it's at least some constant times r to the n. If your Hausdorff measure has that property, then yes, then the Lebesgue differentiation theorem guarantees that porous sets have zero measure. But that's not always true in general. This lower bound on the Hausdorff measure of balls. So this is a condition called lower n regularity, and it's not always true. Yeah. Okay. And okay, so there are some more positive results in somehow like more general setting. So for something called integral current spaces, which you should think of as spaces which come with some kind of metric fundamental class or a kind of orientation. And if your space is a manifold, then this orientation is compatible with the topological orientation. But I think I will skip this. It's anyway quite technical. I guess the only thing I should comment here is that actually this result does allow for the spaces to have boundary, and so as a corollary, you get for example like a strengthening of, or not a strengthening, I don't know, a version of this folklore theorem for manifolds with boundary. So if you have a map between two manifolds or two Riemannian n manifolds, and now you allow them to have boundary, but if they have boundary, then the map needs to respect the boundary, meaning sends the boundary of M to the boundary of N, and then you have, well, I wrote here inequality, but think of this as an equality. So you again have the volume equality, but now you also need the volume equality for the boundaries. And then this forces F to be an isometry. So there is a version of the folklore theorem for maps for maps between manifolds with boundary. And yeah, it takes this form. That's one way to to uh, state it at least. And here notice that I replaced surjective by non-zero degree. I'm not actually entirely sure if I can put surjective here, but this non-zero degree is also pretty common actually in the statements. And actually the folklore theorem is often stated with this assumption, the non-zero degree instead of surjectivity. Okay, so the non-smooth case has to deal somehow with not having this degree theory. And actually, in very, very rough terms, the curvature bound case, at least the non-collapsed RCD case, sort of tries to reduce to the manifold case in a not quite, but it uses this structure theory very strongly that actually you're very close to being a manifold in some sense. There's an open dense manifold so that the complement has very small has codimension 2. And that means that a lot of the curves will be traveling in this manifold where you kind of things are easier. And then also this exceptional cheap set phenomenon, it doesn't happen in these curvature bound spaces. So they have some nice properties in that way. And then for the metric manifolds, you use this theory of integral currents, and the area formula it is still available, and well, then there's some technical connection between integral currents in Rn and BV functions that you utilize. But I will not speak more about that, and instead I'll just mention some open problems to end the talk. Sorry if I'm going over time. I'm not entirely sure what time I started.
No, you're good.
Oh, okay. Well, this is only a few slides anyway. So the first open problem, something I would really like to understand, is this volume rigidity for metric manifolds. So Denny Marty's result was basically this result with the additional assumption of this porous sets having zero measure. But the question basically is, can you remove that? So if you have a one Lipschitz surjection or a non-zero degree map from a metric manifold to a smooth manifold that preserves volume, well, okay, here, let's say closed for this formulation, then is F necessarily an isometry? And this kind of goes back to asking some question about, can you put a metric current structure on this X? You can ask a weaker question. Okay, so let me give up on trying to prove that it's or requiring that it's an isometry. Let me ask, well, for this question, actually, let's even forget that M is the target would be a smooth manifold. Let's take it to be another metric manifold. If you have a one Lipschitz surjection or non-zero degree map between two metric manifolds with the same volume, then is at least this true? Is the length of almost every curve preserved? Well, actually, we already saw an example where this is not true. So the discounted line segment example, I mean, the target is still a metric manifold because it's still Sn. It's a by Lipschitz equivalent, but you don't have this for every curve. But in that situation, you have it for almost every curve. And now you can ask, does this true happen for almost every curve? And just a small remark here. So this length preservation for almost every curve is valid in rectifiable metric spaces, whatever those mean, for those of you who know what that means. So if you have a one Lipschitz map between rectifiable spaces that have the same volume, n volume, then you do get this length preservation for almost every curve. This is not a very difficult result. It's kind of a technical thing when you like play with the definition of rectifiability and use some Kirchheim theory. But the problem is that metric manifolds, first of all, are not necessarily rectifiable. And then also, to go back to the original question, this length preservation doesn't mean that it's isometric in general. And then the very last thing I the very last open question I thought I would mention is this analogous result to the result of Zimbron and Perales and Bay and Connell and the others. Sorry, I forget. There were so many names on that paper. But anyway, for non-collapsed RCD spaces with boundary, do you have an analogous result? So in the presence of boundary, you would require this compatibility so that the F maps the boundary to the boundary, and you have the equality of volumes, but also of the boundary volumes. And that's all. Thank you.
Thanks so much, Terry, for the very, very nice talk. So
Now we
everyone's
can start from the
virtually
beginning.
clapping.
Thanks.
Yeah. So are there any questions before I shoot a couple questions? Yeah,
Right.
Hector, please.
So going back to the first open question, no, your first open problem. Why
Yes.
doesn't the first example, when you have the two spheres with the intrinsic metric and Euclidean metric, is not a counterexample for this? There is something I'm missing. I don't know.
Yeah. So the caveat here is that when I say that M is a smooth oriented Riemannian manifold, of course, well, I mean that it comes with a Riemannian metric, and you look at the distance induced by that metric. So you look at the length distance. So the first counter example that I gave, you had the length distance
Yeah.
on the domain side, and then on the target side,
Mhm.
you put a bad distance. And so the point there is that this Sn equipped with the Euclidean distance, it's not a Riemannian manifold. I mean, it's a manifold, but the metric is not Riemannian.
Yeah. I see. Understand.
Yeah. So this is like a small kind of detail that's easy to miss.
Another question in your previous slide about the sort of the ideas of the proof. You have this exceptional set. How do you
Right.
define this exceptional set? What is going on here? What you're going to measure that is small?
Yeah, so I think so. First of all, I didn't define exceptional chipsets anywhere. It's kind of but what I mean by it is this slide here.
Mhm.
So basically, what I mean is this thing. So by exceptional chipset, I mean a set of measure zero
Mhm.
which affects the metric in the sense that geodesics of
Mhm.
points nearby that set travel some definite distance along that null set.
Mhm.
And so in other words, one way to think about this is that if you're on a manifold and you look at the length metric induced by the Riemannian metric,
Mhm.
so you look at 2 points and you look at all curves, all Lipschitz curves connecting the points, you look at the length and you infimize the length, right?
Mhm.
If I give you a null set on the manifold and I tell you you can only look at curves that do not spend any positive time in this null set, now you have less curves to work with.
Mhm.
But in the manifold setting, you can perturb the curve, like if you like the infimum is still the same because you can perturb any given curve if it happens to spend positive time in the forbidden null set. You can perturb it a little and then it doesn't spend any time there, and then
Mhm.
but the perturbation will have almost the same length. And this is you can kind of perhaps do by hand in some way in the manifold case, but this kind of, if you want to do it by hand, then you're really using the manifold structure and the Riemannian structure very heavily. And so this kind of perturbation is in general not possible in a metric space. And even in the RCD case where it is possible, it's not easy. You cannot do it so easily. It's much more technical to do.
Okay. And one last
Yeah.
question. It seems to me that all this should allow some quantitative statements, no? So I don't know, a cheap one that comes to my mind if it's the Lipschitz norm is slightly bigger than one. So you can quantify the back set in the product where the things are not going to be a little bit far from being anisometry, no? Is that part of the ideas in the proof? Because that's what I was thinking when you mentioned these exceptional sets, but I see that is something different, no? Or has this been tried or
So from these rigidity statements in general, you kind of get some almost rigidity statements um, for free, quote unquote, by using compactness results on the class of metric spaces or manifolds that you're looking at. So what would be true is that, for example, there exists an epsilon, so that if you have a 1 plus epsilon Lipschitz map that between the spaces and the volumes are like the volumes are different only by an epsilon, then the map is obviously not an isometry, but it's almost an isometry in the sense that the distance between fx and fy is at least the distance between x and y minus some epsilon prime or some delta. So you get this kind of additive error. This is possible by those compactness terms. You kind of get without like you get from these rigidity statements directly, but so yeah, that you can do, but it always depends on what kind of almost rigidity you want, right? So for example, let's say you would like a statement to say that if f is almost one Lipschitz and the volumes are almost the same, then my map is like by Lipschitz with constant close to one. Well, this is not true. It's not true even in the one-dimensional case, and if you want it to be true, you need to add more assumptions. So this would be an example of a very strong almost rigidity statement that is too much to hope for. And then actually, it's a very good question, like what kind of almost rigidity you could hope for. But then it also becomes a question of how you quantify the almost equalities, like in what sense you want those. So there are many variants there for sure, and I think it's an interesting question.
Thank you. Very nice talk.
Thanks.
Cool. So, any more questions? I have a potentially silly question. So, do you? Is it worth it to work like in metric manifolds as opposed to say metric orbifolds? Like, do you gain like much from the manifold structure? Like, it seems to me that since like if you had like metric orbifolds, like since the singularities are isolated and this could not be maybe like part of the exceptional sets, and I don't know, maybe this is like a silly.
No. I think so. I mean, the short answer is that I have not. It somehow it kind of hasn't occurred to me to think about that, but it definitely is like, I mean, it makes sense to think about it. Let me ask you a question. Is an orbifold necessarily a homology manifold?
That's a good question, which I forget all the time.
Okay, because yeah.
Maybe
So the reason
yes. Yes.
okay, the reason I'm asking this is that the methods for this volume rigidity on the metric manifold setting, it uses this theory of integral current. So basically, what you want to do is you want to define. I mean, you want to cook up an integral current structure on your metric manifold.
I see. Yeah.
And for metric surfaces, you can always do this as long as the Hausdorff-2 measure is finite.
Right.
For metric manifolds, it's not known if you can always do this. You can do this under certain conditions, like if it's LLC or under this vanishing of the porous sets condition,
Yeah.
and things like this. And the way you do it is you use degree theory for maps.
Yeah. Yeah.
And if the degree theory then the construction therefore works in the spaces where degree theory works.
Right.
And is compatible. Yeah. So perhaps orbifolds would fall into that category, assuming degree theory kind of works.
I see. So
Works
it's
well
so
there.
locally Lipschitz contractible. That's enough.
Locally Lipschitz contractible is probably enough, but LLC means locally linearly contractible. So it's a bit
linearly.
weak.
Okay.
Yeah, yeah.
Okay.
So it's a bit weaker than I think it's a bit weaker than local Lipschitz contractibility. But local Lipschitz contractibility would work, I think. Yeah, yeah.
Okay.
Yeah.
I see. Okay. Nice.
Yeah.
Thanks.
You're
Yeah.
welcome.
So if there are no more questions, so let's thank Terry again. Thanks, Terry, for the wonderful talk.
Thank you. Thank you.
And so yeah, so see you guys in 2 weeks, and I will let you know about the next talk. Thanks.
Okay. Thanks. Thanks.
Cheers. See you guys.
See you.
Bye bye.
Yeah, thanks, Terry. Also, Terry, by the way,
Yeah.
so I think I have the linearity of this differential in the linear cone bundle.
Oh, okay.
So, but
Okay,
I'll
that's
try to
great.
write it down in the next few days. I'm going a little bit slow. Sorry about that.
Yeah, no worries.
Yeah.
Yeah, that's good. That's great. We talked about the thing today with Enrico. And because I mean somehow there was a question of what exactly do we want to include, because we kind
Right.
of have two proofs now, one
Yeah.
using this infinitesimal splitting and the other one using Enrico's argument, but that only works for Alexandrov spaces. But then
Right.
we figured, but actually then we figured that we can actually keep both, because my the infinitesimal splitting stuff, it covers also RCD spaces, but the drawback is that, and also Alexandrov spaces, but only in finite dimension,
Right.
because you need the tangents to have the splitting property, so you need them to satisfy the conclusion of the splitting theorem, right?
Right.
And this is known for Alexandrov spaces, but only if they're length spaces. And
Right.
so there's an example of someone I forget. This was in this book by Alexander and Kapovich and whatever. That if you have a finite dimensional Alexandrov space, then the
Yeah.
tangent space is also
It's
a length
also a
space.
length space.
Yeah.
Right.
But if it's not finite dimensional, then the tangent might fail to be a length space.
A length
And
space.
therefore
Yeah.
yeah, so then maybe that one doesn't have to have the splitting property either.
I see.
Or I'm not sure if it does, at least.
Right.
But then Enrico's argument covers Alexandrov spaces regardless of this. So then it means that it covers also infinite dimensional Alexandrov spaces.
Oh, cool. Nice.
Yeah.
I see.
Yeah.
Okay. That sounds great. Sounds awesome.
Yeah.
Nice.
Cool.
Okay, yeah. So I'll get to work and try to write this in the next few days.
Very good. All right.
Okay, cool.
Bye.
See you
So
soon.
maybe at some point I will, maybe, I don't know when I have time, but I want to have a look at the paper because of yours and the other people, because I'm very interested in this defining like a degree theory of some topological information for
Yeah.
maps. So
So
and I see that you do something like this, right?
yeah, it
So
was an idea of Chris Connell actually, but yeah, he
okay.
has like this like a homotopical index kind of, like a
Mm,
fundamental group index.
yeah.
It doesn't always coincide with the degree, but yeah.
But even in the smooth case it doesn't, or
In the smooth case, I think it does. Yes, it coincides.
okay.
Yeah, but in the
Yeah.
metric case, it doesn't
Not
always.
always. Okay. Yeah. But so it's a very nice. I mean, it's very interesting. I will try to have a look
Nice.
at it
Yeah.
more. And
Thanks.
yeah. All
Awesome.
right.
Yeah. So see you soon, Terry-san. Thanks for the
Bye.
talk.
Bye. You're
Bye.
welcome.
Cheers.
Thanks for the invitation. Bye bye.